Start, I think.
Sure. Okay.
All right.
Uh,
So today we're happy to have here Anthony Sciola for our Space Science Center seminar series. Uh, Anthony is currently a scientist at the Johns Hopkins University APL, where he's part of CGS team. His is focusing on inner magnetosphere dynamic. So, Anthony, if you'd like to start, please.
okay, great. Yeah, thanks very much for having me. Sorry I couldn't be there in person, but I'm happy to talk to you today about some of our recent work on the topic of advances in global modeling of ring current buildup and evolution and decay. And just to say, I'll probably skip through some slides very quickly just for the sake of time, so we have more for discussion. So if I just like blow through a slide and you want to know more about it, then feel free to ask afterwards. But so first to sort of get us started, hopefully everyone's relatively familiar with the ring current. That is one of the sort of major features and components of geomagnetic storms. But I just wanted to quickly highlight that it has many impacts across the geospace environment and many systems that it's coupled to. There's, of course, the strong magnetic perturbation that it causes, both within the magnetosphere, but also on Earth's surface. But also further back on the plasma sheet, tailward of the ring current, this also enhances the magnetic field there, enhancing night-side reconnection and all that. The region 2 currents and conductance via electron precipitation impacts ionospheric current closure and that has certain effects on the shielding of lower L shells. Where's my mouse? There it is. From the convective electric field, which is demonstrated in this plot here with these potential lines of blue getting shielded by this ring current in pink here. And then this in turn affects the location of the geospace plume, the sort of combined plasmasphere and ionospheric plumes shown in black here. And then also the overlap with plasmasphere drives emic waves, which scatters those ions as well as radiation electrons, and also heats the plasma sphere. And so the ring current exists within a very sort of busy system, especially during storms, and is coupled in a whole lot of ways. So the sort of high-level question that we're sort of interested in probing is what governs ring current buildup, evolution, and decay? We can think about this in terms of sources and losses. We know on the source side that earthward transport of the plasma sheet population is the primary source of the ring current, but also that ionospheric O plus and H plus can contribute quite strongly to that. And then on the losses side, we know through modeling studies that magnetopods flow out along open drift paths into the magnetosphere is the main contributor during the main phase, and that H plus charge exchange dominates during the late recovery phase. And that there's a number of other processes that could potentially contribute to the overall losses during the early recovery phase, such as the extra charge exchange due to O plus due to electric cross section, or precipitation driven by emic waves and field line curvature scattering. But the kind of point here is that we have many decades of observational and modeling studies that have identified that each of these things and more are key ingredients during current dynamics. And so the next question of that is to what extent does each ingredient actually contribute to the overall shaping of the storm time ring current? And just for sort of a simple bakery analogy here, if you have the same ingredients, but you have different proportions of each one, you mix them together in different ways, you're going to get a very different result on the other end. And so one of our goals is to dig in more into those relative proportions and how they all interact with each other. So questions regarding the relative contribution can be very challenging to answer with observations alone due to the relatively sparse coverage of in situ measurements and lack of conjunctions of the right sort of instruments at the right regions and times. And so modeling can provide this insight, but modeling the relevant physics from first principles is also a very challenging task. And so due to the coupling between the ring current and those many other physical domains that we just talked about, progress towards answering these questions sort of necessitates a system level scope. And this is true on the observational side and the modeling side. And so what I am going to focus on today is sort of doing a bit of that investigation into the relative roles of sources and losses on ring current evolution using or via case studies using a couple global geospace model. And the two main topics we'll focus on are first quantifying the contribution of mesoscale plasma sheet flows, or BBFs, which we'll define in just a second, to certain time ring current buildup, and then also take a look at how contribution of various sources and losses contribute to the evolution of the ring current energy spectrum in this simulation. And the second is going to be including test particles to investigate the relative roles of neopause losses and charge exchange on the loss of ring current H plus and O plus, and then how those loss processes evolve throughout the phases of the storm. Okay, so to get right into it, but a little bit of background on how we build up the ring current. The sort of classical picture is that there exists this global scale cross-tail electric field that drives convection inwards, and during storms, this becomes enhanced and helps build up your ring current. And so this has been supported by a number of numerical models with outer boundaries at 6 to 9 RE, but it was found later on that when you actually push that intermediate sphere boundary back to 15 RE and try and convect plasma in from there, and also very importantly, more self-consistently include feedback on the ionospheric electric field and the magnetic field, then what they found was that this actually leads to pressure growing too rapidly, and this alters the convection paths and actually halts that inward flow before the plasma can really reach current distances. So that's one sort of problem with this theory, but I think also this is a really nice example of how when you include this more self-consistent treatment and coupling with these other sort of components of the system, you can get very different conclusions from your modeling. And the second sort of problem is that when we've actually gone out to look for this enhanced electric field correlating with the enhanced solar wind driver, we haven't really found it. So the question is, okay, so how much is really coming from this, and where is the rest of it coming from? So one other potential candidate is bursty bulk flows, or BBFs, also theoretically known as plasma sheet bubbles. These are very fast and mesoscale flows commonly observed within the plasma sheet. They are mesoscale because they're about 3 RE or so in azimuthal width. And the video suddenly doesn't want to play. Okay, there we go. So on the bottom here, I have an example of what this looks like in observations of simultaneous signatures and the velocity, injections of hot plasma, and depolarization. But then also on the right here, we have an example of these flows within a global magnetosphere simulation. And so both observations and global modeling have estimated that PBS can be responsible for a majority of the earthward transport of mass, energy, and magnetic flux. But because, and you can see from this video a bit, actually very few of these reach ring current distances, it's still an outstanding question how much they contribute to ring current buildup. And this is, of course, very hard to get at using in situ measurements because we just don't have enough coverage to unambiguously quantify the contribution of many mesoscale flows to a global scale ring current. And there has been a modeling study using a standalone intermediate sphere simulation looking into it, and does suggest that they could be significant contributors. But these standalone simulations have limitations in that they don't sort of include that global scale context, or and don't sort of generate and evolve these bubbles as self-consistently as what we can get out of our global magnetosphere models now. So just a really quick comment on why it matters which flows contribute to ring current buildup. I'm not going to go through this in full detail for the sake of time, but basically bubbles transport particles of different energies and species differently from global scale flows. And so you can imagine if they do transport plasma to the ring current, then which energies and species they transport is going to affect the overall ring current energy spectrum and ion composition. And also they carry depolarizing flux to the magnetosphere, and this alters the evolution and loss of ring current particles after they arrive. And also you can get some dawn-dusk asymmetry effects that are obviously going to be a little less present in a global scale flow. So the study itself that we're going to explore now is looking into bubble contribution to certain time ring current buildup through a case study of the March 17th, 2013 storm. For this, we're using the multi-scale atmosphere geospace environment, or MAGE model. This is currently under active development by the NASA Drive Center for Geospace Storms, or CGS. And also, just a very quick note, this should be releasing on CCMC this week, so you can go ahead and do your own runs on request with this very soon, which is very exciting. But for this simulation specifically, we're using a subset of the full MAGE model consisting of the Gamera global magnetosphere model, which very importantly not only produces these bubbles self-consistently, but also reproduces many of the statistical properties of bubbles as measured by spacecraft such as Themis. And in the nanosphere, we're coupling to the Rice convection model, or RCM, so that we include gradient curvature drifts and can resolve our ring current in an energy resolved manner as well, something that ideal MHD can't do on its own. And then in the ionosphere, we're using the remixed electrostatic potential solver. Just another comment on the coupling is that the ionospheric conductance is being influenced by an empirical electron precipitation model, where that electron source is from RCM. And just a quick plug for some of the other work being done is both Donglin and Shenchen Bao are in the process of developing a new model they're calling Dragon King, which is an advanced precipitation and conductance model, which you'll hopefully hear about more later this year. Okay, so doing a quick simulation overview. Again, going to run through this a little bit quickly, but basically what this analysis of the DST index shows is that we are building up our ring current between 830 and 1030 UT within this full storm here. And so that's where we're going to focus our analysis, of course, of how the ring current gets built up. And I just have an example across this top row here of several different times where you indeed see it being built up over time. But also I chose specific snapshots to show some of these mesoscale flows, which are being indicated here by sharp enhancement in the inward radial velocity, that a number of these do end up penetrating through 6RE. And you can also see down here, it's looking at the perturbation magnetic field. There are carrying some of the polarizing flux with them as well, indicating that these are indeed sort of BBF / bubble structures that we're interested in exploring. So the majority of this analysis focuses on this arc centered with a radius of 6RE along the night side and evaluating different quantities through it. And so here I'm plotting a few things as a function of time on the x-axis and MLT extent on the y-axis. This top panel is the enthalpy flux, or in other words, the transport of plasma energy through that arc. And what we see are many signatures of these injections of this inward flow. Sorry, I flipped the color bars on you here, but I just figured earthward should be positive since we're talking about contribution to the ring current here. So the red is earthward flows for these plots. And then we also see that they are quite narrow in width on the scale of several RE, but also that they have these return flows on either side of them, because as these bubbles come in, they end up interchanging with the background plasma that was there and had some plasma pressure on them, and so it kicks those guys out. And I completely exited my presentation. Cool. All right, we're back. So the plot below that, we're also showing that there's simultaneous signatures of depolarizations and depletions in the flux tube entropy. These three things together are indicative of these bubble structures that we are investigating. Also, really quickly, if I do a quick summary or a quick integration of the total energy as it crosses this arc, we find that the energy flux is primarily in the form of enthalpy flux, or it's already in the form of plasma energy as it goes through that arc, only then followed by the flux of magnetic energy. So to actually quantify the contribution to ring current buildup, basically we have this algorithm for picking out both the bubbles themselves and the regions on either side of them to include the effect of those return flows, because they wouldn't be occurring without the bubbles. And so what we find is essentially that half of the plasma energy that is crossing through 6RE and being available to the ring current is indeed coming through these mesoscale flows, these PBFs or bubbles. And so going back to that slide I shared earlier, this then means that this likely has some significant implications on the ranges of energies and also the function of species that have access to the ring current. And that's something that we hope to explore in more detail in the future. Just also another note about these return flows, we find that they end up transporting outwards, an average of 40% of the thermal energy being transported inwards by the bubbles. And this is just an important factor to consider when quantifying the net contribution of bubbles to the ring current buildup, because if you just consider the earthward flows, then you're going to overestimate their contribution. That's an important point for future missions that hope to quantify this observationally. But now to get into analysis of the energy spectra we're getting in the inner magnetosphere, we'll start with this data model comparison between the proton intensities coming out of the RCM inner magnetosphere model and those measured by RBSP-B, the RB-SPICE instrument on RBSP. On the left, we are looking at the energy spectra from 10 to 200 keV, and then we also have select energies picked out here. And it's also video, so we can get a context of where we're at in the simulation relative to these measurements here. But overall, it's sort of showing that we're getting really good agreement across this energy range most responsible for ring current buildup, and that we're also capturing sort of the high-level features such as the ring current magnitude and location of the inner edge here. But so this is a very good agreement. I think one of the better agreements between data model comparisons as far as ring current intensities go. And so it's, what's really nice about it is that, certain features sort of stand out to you. And so you sort of ask, well, why are we missing this high energy background that seems to be there in the data? Or what is this feature coming from here? We have a little more deeper analysis of this, but just to sort of summarize it, having these discrepancies at certain locations and energy ranges are able to give us actionable insight into, these things that we need to add to the model for improvement and better agreement in future simulations. And so now to actually look at the evolution of the ring current energy spectra, what I'm doing here is I am probing these three stationary points here. This innermost one is at 3.8 RE, and then they go back to 4.3 and then 4.8 behind that. And I chose that because this inner point at this specific time in the simulation is where we're seeing the peak ring current. So that's where we want to sort of probe and see how the system evolves from there. And what I'm actually showing on these panels is the cumulative pressure as a function of time on the x-axis and then as a function of energy on the y-axis. So the cumulative pressure as a whole is the color contour, and then these white lines are the median and quartile values of the cumulative pressure. So in other words, this 50% line in the middle, or the median energy, as we'll call it, is indicating the energy at which protons below the energy are contributing 50% to the total ring current pressure. So what we see if we just focus on this top plot is that at the period of peak ring current energy around here, about half of our pressure is coming from protons 20 keV and below, and then throughout the next sort of 9-hour period, that increases to a median of 70 keV. And so this sort of general trend is very similar to what's been identified both in case studies, such as the one by Keika et al. 2018, but also some statistical studies using the Allen probes by Zhao and Giolito here, where we see sort of pre-storm, the energy content is coming from these very high proton energies, and then during the storm, it dips quite substantially, and then gradually goes back to pre-storm values as it recovers. And the magnitudes aren't quite right here. Similar to what we noticed before, it doesn't seem like we're starting with enough of a high energy background population to sort of get us up to that multi-hundred keV to start with, but we are at least producing this general trend, and hopefully with those additions in the future, we'll be able to quantitatively produce these statistics a little bit more. But then this question asked from here is what processes are responsible for this evolution? So what we have here is looking into sources and losses contributing to the evolution at this 3.8 RE probe point. The first thing we look at is just the total energy flux through that 6RE arc once again, but over a longer period of time, to sort of get at how maybe transport of new plasma affects this. And we do indeed see, after this initial ring current buildup, we have a number of impulsive sort of enhancements in this median energy, particularly at these two right after initial ring current buildup and this one later on, that correlate pretty well with enhanced periods of inward transport. And so the sort of implication is that the plasma sheet is getting hotter throughout the storm, and then this gets communicated to the ring current via earthward flows. This is very similar to the conclusion made by Keika et al. On his case study. But to take a look at potential losses, what we've done here is we're now just plotting the intensity as a function of energy and looking at two energies specifically, both 10 and 50 keV. And looking at those is just time series down here. And quick note, this is on a log scale. What we see for 50 keV is that once it gets built up, it stays relatively constant throughout this period. It does decrease a bit over time, but not nearly as much as is the case for the 10 keV protons. Where they decrease much more strongly throughout this period. So if you do a quick back of the envelope calculation, this relative difference between the two is consistent with what you expect from charge exchange. And so basically our sort of initial conclusion from this is that the contributors to the evolution of the energy spectra is a combination of these impulsive adjustments through periods of enhanced inward transport of the plasma sheet, combined with the more continuous effect of energy-dependent charge exchange. But two important sort of caveats to this is one, we aren't really considering contribution from other loss processes in this. You could make a similar argument that differences in convection and menopause losses could potentially lead to a similar feature. And so it's unclear here how much that actually contributes. And also we sort of, implied this connection between the plasma sheet and ring current. But as we showed earlier, we really want to investigate how those different energies are actually making it to the plasma sheet in the first case, and then transported to the ring current to make a more quantitative connection between these two. And so this sort of motivates the sort of deeper understanding that we want to dig into in the future, into quantifying more directly the contributions of certain sources and loss processes to the evolution of the ring current energy spectrum. Also, for the sake of time, just to make sure you have enough time for questions, I'm not going to go through the slide, but I'm basically making the same, argument as before, but just even more so, it's even more challenging to get all this right within a global Newstra model, because not only do you need to have the right sources and losses in there, but they need to be moving the right plasma energies and species in the first place to actually reproduce what's going on in reality. So this is quite a challenge, but something that we're working on. And also, a sort of positive of this is the more sort of sources and losses we add into the model, it also increases the number of ways we can validate our model. For example, we can calculate synthetic ENAs from the simulation and compare with spacecraft like TWINS and HINA and MENA and all that. We can also look at things like ion precipitation, warm electron precipitation, see where suborbital red arcs are forming, seeing if we're matching with that in our simulations, and sort of gaining all these sort of leverage points to sort of scrutinize the model and then improve it where we can. And then down the road, we can use that to get some insight into these observed statistical trends of the evolving energy evolution. But this also motivates our next study, which is investigating the relative roles of ion loss processes on ring current H+ and O+ evolution. So we're not getting to all those major questions right away, but this is progress towards being able to do that. That's just as a quick overview. Again, we know that the dominant loss process during the main phase is due to menopause losses, and it is expected to contribute to some degree to the early recovery phase. During the late recovery phase, charge exchange of H+ dominates, although you also have O+ in there with faster charge exchange rate, and so it's unclear how much that contributes to the early recovery phase sort of decay of the ring current. And another possible contributor to that early phase decay is ion precipitation. Another important aspect of ion precipitation, which is, I should say, due to pitch angle scattering driven by either emic waves or field line curvature scattering, all these have their own energy dependent influences on the ring current. Some are strong at certain energy ranges more than others. But also as a whole, this is expected to contribute to early recovery phases as well. And so I think this is a really good example of some of what we're talking about, of trying to do these relative comparisons and really get at what the major contributors are. But just 2 points I'll make is that so far the ENA coverage we have does not cover the entire ring current energy range. You can see, at least for the studies used here, it's only looking at the lower end at 20 keV and higher, and so we're not getting potentially quite a lot of the plasma that could be contributing to the total ring current energy. And also the modeling studies that have been done on this so far have predominantly been done using standalone NMR for models, which rely to some degree on empirical ionospheric electric fields and magnetic fields, and are overall less self-consistent than a global coupled model. And so they don't, for example, fully model the feedback of the evolving ring current on those fields and how that in turn impacts losses and sort of loops back on itself. And of course, this is not to disparage these studies. They've done a lot to improve our understanding of these loss processes. But now with our sort of improvement in modeling capabilities, you want to take this a step further and investigate these within the more global context and more coupled system. And so that brings us to our next study here, where we are again using the MAGE model to do a storm simulation, but then also seeding test particles throughout it, and then tracking their evolution and losses to the system to get a read for how much that is coming through magnetopods versus charge exchange losses. And so for this, we're trying to investigate how the relative contributions of these loss processes evolve throughout the storm phases, and to what extent do the relative contributions differ between O plus and H plus. And it's just a quick comment on how we're doing our test particle seeding and weighting. We seed all of them at 15 RE in the tail, and then let them be brought inward by these inward flows. And because we are not doing guiding center but full orbits, then they can be non-adiabatically energized and scattered as well, which is quite important for the O plus population. And then we are weighting them using the MHD density and Maxwellian temperature. But because we also need to partition that single fluid, those single fluid moments between O plus and H plus, we are using measurements from MMS to do that essentially. And you can see here that throughout the storm, it sort of ramps up from 0% to about 20% ratio between O plus to H plus at 15 RE. Okay, so to go over an overview of the run itself and test particle results. The top here, we're just looking at what's produced with the fluid model on its own, where we have, in theory, magnetopause losses and charge exchange included, but not some of those others like ion precipitation, certainly not from the EMIC waves quite yet. But up here, I am showing a comparison between the observed and modeled SMR index, which is sort of analogous to SIMH. I'm showing both the actual value and then its time derivative here. And basically what we see is that the model is reproducing timings of ring current growth and decay, but sometimes underestimates the magnitude. And particularly looking at when we're going into the recovery phase here, we see that we're underestimating that delta SMR as we're going into that early recovery phase. And throughout a bit of that early recovery phase and only agreeing later on towards later steps. And so this could be indicating that that the inclusion of ionospheric precipitation or O plus may be what we need to improve this agreement on the fluid model or within the fluid model. On the test particle side, down here, I'm showing the test particle energy sort of rate into geo. We see these two spikes here that correlate well with the decreases in SMR. And then similarly below that, I'm showing the total kinetic energy of the active particles within geo. And so when we include the O plus test O to H plus weighting for the storm, we see that the majority of plasma energy is carried by the H plus. This is qualitatively consistent with the comparison of ion intensities done by Lynn Kistler last year in her 2023 paper. And so if we look at the test particle losses on their own, going a little too fast. On the top here, we have a SMR plot again. And then I'm also showing the solar wind drivers, the solar wind EY and dynamic pressure here to sort of give context to the sort of structures we're seeing in the loss rates on the bottom. And so what's immediately apparent is that magnetopause losses dominate throughout the entirety of the main phase, and also that the magnetopause losses have a lot more structure to them and a stronger response to the solar wind drivers than the charge exchange rates do. However, it's quite possible that there could be clear signatures of the driving conditions present in the energy spectra of the charge exchange losses. And of course, that's something that we want to look into in the future as well. And then we see as the solar wind electric field decreases and dynamic pressure decreases, then charge exchange begins to dominate. Now, if we include the effects of O plus as well, the first thing we see, this is the same plot as the previous page, but including O plus losses as well. What we see is that despite O plus carrying less of the total plasma energy to GEO, the energy lost due to charge exchange rates are very similar to H plus. Now this may seem kind of intuitive at first because the O plus charge exchange cross section is larger, but that isn't the only difference between these two populations. O plus has come in and has become on average more adiabatically energized and scattered, maybe have different distributions in the magnetosphere, and so it's not necessarily obvious that this would be the case. And so, but we do have some more digging to do there to see how those sort of factors all play into it. And if we look at the relative contribution of charge exchange versus the total losses for both of these species, we see that, again, O plus is consistently greater. Charge exchange contribution is greater for O plus than it is for H plus. One of the consequences of this is going into the early recovery phase, the O plus losses actually become dominated about 2 hours before they do for H plus, which is kind of interesting. So if we sort of package this all up and look at the overall contribution, and here I'm showing the same information, but just sort of as a cumulative plot to see it all together. These preliminary results are supporting the conclusions made by some modeling studies of Takahashi et al. And Limon et al. That menopause losses do dominate during the main phase and contribute to an extent to the early recovery phase. However, we need to include other factors such as ion precipitation to sort of capture those effects as well. But we also see that during the main phase, the charge exchange loss rate for O plus and H plus are comparable, but the O plus loss rates don't extend as far into the late recovery phase as they do for H plus. And so just a sort of qualitative analysis here, we sort of see that the gradual fall off of menopause losses for both H plus and O plus, as well as O plus charge exchange, seem to be contributing to that transition between early and recovery phases. And so the next step is to sort of more quantitatively do this analysis. Also, once we have the ionospheric precipitation in there as well. I do have some very preliminary results on the FLC losses, but it's just too much to go into today, so we're going to skip it for now. But okay, so if you've seen me present in the past year or two, there's a good chance you've seen me present the ring current buildup work several times. So thank you for listening to it once again. But I also want to share some of the future work that we plan to do, sort of that's been motivated by these two studies here. And they're both in the spirit of trying to quantify the source and loss contributions to evolution of the ring current energy spectrum. On the sources side, we plan to quantify the contribution of the evolution and transport of the plasma sheet population to the evolution of storm time ring current energy energy spectrum and ion composition, and more specifically, track the evolution of that plasma sheet population over time and how preferential transport between global scale flows versus mesoscale flows affects the energies and species that are able to reach the ring current. And on the loss side, we plan to quantify how the major loss processes act on the ring current as a function of energy, investigate how the system state, which includes not just the convection strength, but also the distribution of that convective electric field throughout the magnetosphere, but also the degree of magnetic depletion impacts their effectiveness and how all this sort of feeds back on itself through the evolution of the ring current. And also, another thing that we plan to investigate is to compare the loss rates derived from our test particle experiments to parameterized estimates that are very commonly used in fluid and bounce average models. And what sort of motivated this is we found that when we calculate the charge exchange rates on our test particles, where we can actually probe exactly where they are and what the neutral background is, we see that this gives us a sort of different overall rate than what some of the parameterized estimates are that are commonly used in fluid and bounce average models, specifically the one that's very commonly used for off-equator charge exchange rates from Smith and Butra. And then because of that difference, we also want to explore that for FLC scattering rates as well, some parameters estimates that exist there. And so hopefully this will give us an even better description of the losses that we can then incorporate into the fluid and bounce average models. And for bounce average, I'm referring to the RCM, which is a bounce average inner miniature model. But this is also very timely to dig into these sort of details, because we're also in the process of developing a brand new intermediate model. We're calling this the ring current advection integrated over J and U, or RIJU model, which is quite an acronym. But basically, this model inherits the physical formulation from RCM, but has a completely rewritten numerics and a model infrastructure from the ground up. One of the main motivations for this is that we are designing this with multi-scale whole geospace modeling in mind sort of from the start, as opposed to some of the other intermediate models, especially RCM, that was designed with sort of standalone self-consistency in mind in a lot of its design decisions. But now with this different approach, we're able to sort of optimize the model for this global geospace coupling. And so that means we'll be getting a major performance boost that will improve the model runtime overall, so we can do longer and high resolution simulations. We're upgrading the core numerical solver to be similar to those the high quality numerics used within Chimera. And this also allows for a more integrated information transfer between the different models. And we'll use this to gain a higher spatial energy resolution, and particularly concentrate a lot of our grid resolution in the auroral region to capture those mesoscale features in the aurora. We'll be able to do things like calculate losses at every single sub-time step of the model. It's kind of getting into the details, but basically be able to do it at a higher cadence than what we can do now in RCM. And we'll be able to do things like utilize the full field tracing information to improve our calculation of losses as well in the model. Also, we're simultaneously working on developing multi-fluid capabilities for Chimera. And so this, with coupling with RIJU, will allow for better handling of plasmasphere and solar wind H+ as two distinct species instead of one, as well as let us include O+. In addition to that, what's also being developed right now is the hydropolar wind model being led by Roger Varney out of UCLA, which will provide high resolution source of ionospheric O+ outflow. And so down the road, we'll be able to sort of couple all this together and do some really cool science with that. So just a really quick look at the state of RIJU development, just to show this not just proof of concept, but we're making some progress on this. We're currently at the stage where we're doing some standalone one-way driving experiments. Right now, we are just testing out the information transfer between the models, and there's still some physical constraints to add onto the system. So don't take sort of the specific sort of structures you see in here too seriously, but this is just to show that we are indeed communicating information from the MHD model to RIJU and making good progress on that. Okay, so to sort of wrap things up, the sort of theme we were sort of covering here is that we have a good understanding of what the key ingredients are during current buildup, evolution, and decay. However, how much each one of these ingredients contributes to ring current dynamics, how they interact with one another, and how they're dependent on some specific conditions are still major open questions. And those are the types of questions that we're particularly interested in exploring with our geospace model. Some of the specific results we shared today were that bubbles can indeed contribute significantly to the ring current plasma energy buildup, and therefore this sort of warrants follow-up investigations on what that means for the evolution of that energy spectrum and ion composition throughout the storm. we showed that return flows are very important to consider when quantifying the net contribution of bubbles to the ring current. This is especially important for future missions that help to quantify this, or future models that quantify it in their simulations as well. And that also, for the most part, the model is accurately reproducing observed storm time intermediary characteristics, including signatures of injections, the overall ring current location and intensity, as well as energy spectra, and that the discrepancies at certain locations and energy ranges are, sort of minute enough to give us some actionable insight into places for model improvement. And then, with all this, we'll have a better sort of ring current energy spectra to feed into these lost models and get a better understanding of the relative contributions of each. And then, of course, digging into how, again, this is all coupled together and feeds back on subsequent evolution. And then finally, we're working on the development of Raiju, which will provide both physical and performance improvements to Mage's ability to understand the ring current as a major component within the highly coupled geospace system. So that is all I've got. Thanks.
Right. Thank you, Anthony.
Mhm.
If someone have any questions, you can unmute yourself or write in the chat. Is there anyone in the room, Nick?
Hi, quick question. It's
Mhm.
from UNH in the room. Can you walk us through one more time how to for the given spectra or like other plots, how to identify the bubble-like features? I think you had a couple parameters showing like BZ or like VR. Can you go to one of those slides and
Yeah, for
help us
sure.
identify the
Yeah, so I'll jump to what we see in data first really quick. So you see a simultaneous flow burst or enhancement in the radial velocity, but also in the temperature of the plasma it's pulling in, and also enhancement in that BZ relative to the background there. And the way this sort of looks in the model, sort of one way, sorry, it's not the one. Yeah, this is the one I want to show.
yeah.
So this is, let me jump back too. So this is looking at the delta BZ. So it's BZ with the dipole subtracted out. So we're just seeing the perturbation magnetic field. And so during storms, this gets depressed at 6RE. But so you see where it's white, then it's becoming back to sort of zero perturbation, which is dipole strength. So which is why they're called dipolarizations.
Ah. Okay, yeah, I was
Yeah,
confused. That makes sense. And
yeah,
that
no problem.
correlates to, wait, that should it correlate to injection site? Shouldn't it be like off of that spot?
So yeah, so it does get more complex with the actual structures themselves, in terms of the sort of dipolarization front and the structure throughout the bubble itself. But yeah, another thing about these injections too is this is just looking at the transport of plasma energy. So another effect that you can get from these is that these bubbles can sort of snowplow some of the flux loops in front of them, and so you can get an enhancement in the inward transport of the plasma energy before you actually see the bubble itself. Um, yeah,
Gotcha. Thank
I don't know
you.
if that quite got your second part of the question, but
Yeah, definitely. Thank you.
cool.
I have a question. This is Lynn Kistler. Can you go over again how you do the charge exchange? That's done from a full particle simulation, but from that you're getting a full energy spectrum and you're integrating it over that whole energy spectrum, or
Yeah, so basically, I don't have a maybe a plot to show it in this presentation, but basically, at every point in time as we evolve the particles, we know the location, the energy they have, and so we are essentially using the hydrogen and oxygen cross sections from the Smith and Butra, as well as the Oscard geocorona model. And so since we know the location, we can evaluate what the neutral density is, and we calculate the charge exchange lifetime from that. And then, based on the DT of the particle, how frequently we sort of apply this loss, which I think you were doing on the order of 30 seconds or so, we calculate the amount of the particle weight that gets lost and the sort of energy that comes along with that based on whatever energy the particle had. And so the plots that I showed specifically is integrating over all the different particle energies to get just the cumulative effect of each one of these. But in theory, we do have that detailed information that we can explore more in the future.
And is this this is integrating both in energy and also in space over the whole?
Correct. Yeah. Yeah. This is just the total losses here. Because you have, so it's quite a big parameter space to sort of evaluate, and there's, plenty of extra sort of detail and nuance in those as well. Yeah, so this is something that we're planning to dig into in the near future here.
Yeah. Okay. Yeah, that's great. I have one other question. It's
Mhm.
I've always been intrigued by that Horry paper that you
Mhm.
showed at the
Yeah.
beginning. And clearly in the inner magnetosphere, it's very clearly observed that the electric field increases,
Mhm.
right from.
Yeah, and I think that's much
Right.
more clear in the Roland and Weigand paper as well, which I think I also cited here. That's
Right, but
before
also
you
it's been
asked whether
done
that
with
does.
EDI, with the cluster measurements and the Weimer stuff also. So do you
Mhm.
understand the Horry result? Why he
So,
doesn't see anything?
I mean, it's a good question. I forget exactly what radial distances he's looking at in this, but I do believe they're beyond the sort of 6 RE or so. So they are further out in the tail, I think out to up to 15 RE. And it is true that there are, definitely instances where we are seeing enhanced electric field here, but we aren't seeing, a really obvious and strong correlation with the solar wind driver.
Right. I'm betting your model you have a strong correlation with the solar wind driver.
So this is, they're specifically trying to get at the global scale field, which is why they're doing this 20-minute average here. So they're trying to sort of filter out any of these smaller spatial scales through this 20-minute averaging here.
Anyway, okay, thanks.
Yeah, no problem.
Something that you always love. Horry was geotail for the out in plasma sheet. Okay. All right. Any other question? So, all right. Thank you again, Anthony.
Okay, cool.
Pleasure
Thanks very
having
much.
you.
Thanks for having me.
All right.